So we're going to finish 4.1 by looking at the effects of A on the graph. So I'm going to keep writing this in function notation, even though our textbook uses Y. It doesn't particularly matter. It's just, I think, easier to use function notation. So we're going to graph two different equations. So we're going to graph f of x equals the positive 16x squared plus 1450, and we're going to graph, I'm going to name it g of x. They're using y's, y1 and y2. That matches what's in a TI-84 graphing calculator. I think the Desmos is a little more powerful. And we're just going to see what happens here with A. Now let's remind ourselves what A is. A is the term, is the coefficient in the quadratic term. So for this function, for f, it's 16, and for g, it's negative 16. Notice they're opposite values. So what do we think is going to happen? Well, I've already got this first one as h of x. I guess we'll change it to f of x. And I'm going to get rid of this table. We don't really need it right now. And then I'm going to put in g of x, and this is going to equal 16x squared plus 1450. Ooh, what happened? Well, the function with the positive coefficient, the positive 16, opens up, and the negative 16 opens down. So there's your connection with a quadratic function. Positive a's, so we'll say it like this: when a is greater than 0, the parabola looks like this. When a is less than 0, the parabola looks like this. So we could say opens up. Here we could say opens down. All right, and then for number 10, so this was all number 9. I forgot to label that. I'm sorry. So for number 10, we're now going to look at, well, what happens with the size of A? What if we make A larger or smaller? So they're asking us to focus specifically on the negative 1, and they want us to graph negative 16x squared plus 100, and then negative 6x squared plus 100, and negative 40 plus 100, x squared plus 100. So let's go check those three graphs out in Desmos and see what happens. I will change this to 100 here. We'll change this one to negative 6 plus 100. And finally, we'll do h of x equals negative 40 x squared plus 100. And then we're going to have to change this. We don't want to go from these values. Let's go from negative 50 like we had before up to 120. There we go. Okay, so here's our beginning graph, negative 16x squared. When we make that coefficient smaller, really it's larger because negative. So when we go from 16 to 6, look what happens. Ooh, it got wider. And then when we went to 40, the U got narrower. If we ignore the negative signs, so if I got rid of these negatives, we'd flip them all up above, and then maybe we could talk a little more about wider and narrower. So when we make the coefficient smaller, when it's a positive value, the graph gets wider. When we make it larger, the graph gets narrower. All right, let's write that down. So in general, when the absolute value of A becomes larger, larger referring to, let's say, larger than 1, then the graph, this pen, becomes narrower. Let's not say graph, let's say the parabola is narrower. And then for smaller values, so for smaller a's, the graph becomes wider. If you look at the blue box on page 397, it says the third line, the magnitude of A affects the width of the parabola. The larger the absolute value of A, the narrower the parabola in general. So I'm going to let you all run through 11 a little bit on your own and try to predict that. And then maybe in class, or you could email me what your predictions are, and we could see if you're correct. And the final thing we're going to look at is what's the effects of B on this graph? So we're told to assume for the time being that you're back on the roof, and instead of merely releasing the ball, you throw it down with an initial velocity of 40 feet per second. So throwing it down gives us, your textbook writes it like this, HD of t for down. And notice that that velocity of 40 feet per second shows up right here. So there's that 40 plus 1450. And then what if we throw it up with a velocity of 40 feet per second? So if you think about what's happening here, we're on this building, and for the H down, instead of just releasing it, we're throwing it hard down that way. And then instead of throwing it down for this up one, we're throwing it up. And if you remember what's up with gravity, eventually gravity will slow that ball till it stops, and then it will begin falling again. So we're not throwing this in this direction. That is not happening. We're just throwing it down or throwing it up. So let's look at what happens with the graph of these two. So here's this. We need to make this negative 16x minus 40x plus 1450. And I'm going to go back to, 1450. I'll go back to the same things we had before. I'm going to copy and paste this here as if I thought I was going to do it. Okay, we're just going to duplicate this, and we're going to change that to a plus sign, and then we're ready to go. And if we remember the restrictions on the domain here, it was negative 10 to 10, and here was negative 50 to 1500 for that nice, neat view of the graph. Ooh, what happened? Let's see. So here's the initial one, and there's the change. Let's duplicate this, and let's take away the plus 40. So here's the initial one. Boy, they're all the same color. Isn't that awful? So here's when we're not throwing it with a speed down. And then when we throw it with an extra speed down, notice it gets to the bottom faster, which should make sense. And then if we throw it with a speed up, it takes longer to get there. In fact, the height goes above 1450, up to 1475 in this case, and then it begins falling over time over here. Just in case you're interested, you can, where is it? You can do this, and you can click here, and we can change the colors so that these look a little different. There we go. All right, so let's summarize that. What did B do? So it turned out, really, all the textbook wants us to note is in the blue line there. When B was 0, our height was on the y-axis. It was the y-intercept. When B was not equal to 0, the largest value was not on the vertical asymptote. So I'm going to write this down after number 13. So if B equals 0, they're calling it the turning point. That's meaning this point here. If it had been a positive one, it would be that point here. So the turning point is on the y-axis. And then if B is not equal to 0, oh, you can't see what I'm writing. So if B equals 0, the turning point, which is this thing or this thing, depending upon whether you have a positive A or negative A. We look just at negative A's. It's on the y-axis. If B doesn't equal 0, then the turning point is not on the y-axis. So that's it for this section. I want to point you to a really nice feature of these textbooks. This summary gives us a nice kind of overview of all the things we just looked at. A quadratic function comes in this form, where these things are coefficients of real numbers, and you can't have a, b, and 0. The shape of that graph, we call it a parabola. And the graph of a line, we call a line. And the graph of an exponential function, we call a curve. And then we know that if A is positive, this thing opens up. If A is negative, it opens down. We know the magnitude of A messes with the width of this thing. And then we know that the turning point of the graph is on the y-axis if B is equal to 0, and it's not on the y-axis if B is not equal to 0. And then we know that the y-intercept, or the vertical intercept, is always 0, c. This is unchanged, by the way, even if we change B. It just turned out that the turning point was 0, c if B was equal to 0.